Assalamualaikum warahmatullahi wabarakatuh, and salam sejahtera to my friends and to my lecturers. My name is Azidi bin Yangsan. I'm from section 8. Today I want to introduce about the 3D printing in manufacturing. First, 3D printing. 3D printing is additive manufacturing. It is a process of making three-dimensional solid object from two digital files. Additive process an object created by laying down the successive layer of the material until the object is created, and each this layer can be seen as a tiny slice cross-section area of the object. 3D printing enables you to produce complex shapes using less material than the traditional manufacturing method. Next, we talk about manufacturing. Manufacturing is a comprehensive industrial process which is previously sold one or non-functional product of component or in return to a new light or better than new condition and warranted in performance level and quality. This process same as recycling or repairing. Most commonly manufacturing product categories are aircraft component, automotive part, electric and electronic equipment, engine and component, and medical equipment. Okay, next we talk about the manufacturing process. There are four stages that manufacturing process that can use on the used product to become a manufacturing product. So the first stage is inspection or grading, second stage is disassembly, and third stage is component reprocessing, and fourth stage is reassembly and testing. So first stage in manufacturing process is inspection grinding process. First, the user product need to be inspected for their quality condition, for their manufacturability status. Second, and then the process usually involve the complete the visual inspection. After the inspection process, user product are considered either as a scrap or the manufacturable product. If the user product is scrap, are either disposed or sold to the scrap broker, where manufacturable are sent to the assembly and inspection process at the second stage. So the second stage of manufacturing process is disassembly and inspection process. The manufacturable item could be disassembled into a module, which is further disassembled into the individual component. Inspection of the constituent component can either take place simultaneously and sequentially. The time taken the assembly and inspection process depend on the quantity of the manufacturing product. Then component grade as manufacturing or scrap. Okay, the third stage of manufacturing process is reprocessing of manufacturing constituent component. This process involves cleaning, repairing, suffering, finishing, and aim to restore the component to their original condition. The number of process and time required reproduce each component to the original condition depend on the quantity of component and the component with complex design multiple steps such as welding. Cutting might be necessary in order to restore to the component to the original condition. Okay, the last stage of manufacturing process is reassembly. This process is reassemble of disassembled component from the stage 3 into the remanufacturing product with a simple structure. The reassemblability time can be improved with highly skilled worker for the reassembly process. Next is 3D printing in manufacturing. Remanufacturing traditionally involves removing material for restoring, but processing like 3D printing and additive manufacturing are offering way more to increase useful life in the used part. The additive manufacturing process such as laser sintering and the thermal sparing are being used in the remanufacturing process to bring one part or core back to the original dimension. 3D printing also has been used as a better way by remanufacturer. There are two primary rules for additive manufacturing in manufacturing. First, some additive manufacturing process make a standalone part but can also be used applied to the existing part to repairing damage. The other additive manufacturing process is making miserable internal component via 3D printing. Next we talk about the directly energy deposition (DED). These are 3D printing technique based on automatic welding and technology for replacing missing, broken, and worn metal part, usually construct with a nozzle, a multi-axis arm, which deposit a melting material onto the surface, where it's hardened. DED also help to create a complex part with a small amount of time and the custom part that no longer have been made. This process also can be used with a polymer, ceramic, but is typically used with a metal in the form either powder or wire.
Hello, my name is al-Nabil, and now let me explain to you the process of remanufacturing. Remanufacturing consists of four stages, which are inspection, disassembly, remanufacturing or repairing process, and lastly, assembly. Each stage is important in order to ensure no further damage to be done in overall process. The process begins by inspecting the damaged part to determine the feasibility to remanufacture using 3D printing. So, the main question in this process is, can it be 3D printed? Remanufacturing using 3D printing are not applicable to all parts and components due to the limitation of mechanical properties, which depends on the material used and also the bonding strength of the 3D printed part. However, certain parts can be 3D printed as long as it does not affect the performance of the part. Usually, the parts that cannot be 3D printed are high impact and high risk of failure, which means their usage are very high. For instance, a defected aircraft engine mounting bracket cannot be 3D printed as the whole part is critical in delivering the purpose of the bracket. Small defect or alteration can affect overall performance of the bracket, leading to increase in risk of failure. This is a spur gear on a shaft. As I zoom in to the gear, this is the damaged portion on one of its teeth. This damaged part needs to be prepared as it would affect the mechanism which uses this gear. Before we proceed, we need to know if this gear is feasible to do 3D printing remanufacture or not. Well, this gear is a low impact as it does not experience any high stress or strain under working condition. Therefore, this gear is feasible to do 3D printing remanufacture. Next, we disassemble the gear from the shaft so it would be easier to work on the gear. Otherwise, there will be damage on the shaft if not handled properly. Then, we prepare the surface to deposit material on it by grinding off the damaged part into smooth flat surface. Grinding must be done properly to prevent damage on unaffected parts. This smooth flat surface is then cleaned to ensure no debris or residues before depositing material onto the surface, which will cause defect later on. After that, new material will be deposited onto the surface. For this gear, we use laser metal deposition or LDM to create no teeth for this gear. The LDM extrudes metal onto the surface, and the movement is controlled by G-code generated based on the shape of the teeth. The LDM creates the exact same shape of teeth as before, thus reducing any material waste. The new teeth is now created, but it needs finishing by sanding off excess material for much smoother surface. As you can see here, there is a difference in terms of the look. This is because the material is not the same as the original, but the new material has similar mechanical properties as the original one. And now the gear is ready. Okay, now we move on to real world application. Thank you.
Hello everyone, my name is Kahishwini and I'm going to talk about the application of 3D printing for remanufacturing in the current world right now. So what I'm going to talk about is some of the machines and the methods used, as well as some of the application that has been applied by the industry. So the first one that we see is laser metal deposition, LMD. The picture that we are seeing is the LMD method being used for a blade tip repair. So what is LMD? LMD is actually the process of using a laser beam to melt a metal filler or a powder to form a deposit that is actually fusion bonded on a metallic substrate with a controlled heat input. And also the materials that can be used for this is titanium. You can use nickel, cobalt, and also steel alloys. They can be deposited onto a substrate to create a brand new surface. You can also use it to restore worn surfaces or to apply material to clad a specific area of a component. This LMD is actually computerized, meaning that all the movements and all the parameters, they're actually numerically controlled. This is actually to ensure the precision and the accuracy of the deposition process. This technique is applied very widely in aerospace, machinery, marine, and also the oil and gas sectors. A very widely known application is the use of LMD for repairing high pressure compressor blades in aircraft engines. One of the reasons for using this LMD process is because it really opens new opportunities, especially for repairing components which are considered non-repairable by the conventional high heat input method. And this method can actually achieve up to 50 to 70% cost saving compared to the cost of buying a new product. New technology developments in the current market right now includes the combination of LMD with conventional machining processes, so that some machines can create a hybrid additive and also subtractive process, which can allow material to be added or removed in a single setup, and this really leads to greater flexibility and savings in terms of both cost and time. Now I'm going to talk about the robotic high pressure cold spray. Conventional thermal spray process actually has been used by the industry for restoration of surfaces on worn components, but the use of this process is actually very limited because of the high heat input, which causes a lot of residual stress in the coatings, and it also limits the thickness that the user tends to obtain. cold spray, on the other hand, is actually a very high kinetic energy coating process which uses powder particles, and the size of these particles are between 10 to 50 micrometer, and it is accelerated to high velocities between 200 to 1000 meter per second by a supersonic compressed gas jet at temperatures that is below the melting point. I'm going to talk about the process a little bit. What happens here is upon impact with the substrate, the particles actually deform and they create a bonded coating. As these particles remain in the solid and quite cold stage, they impart a little oxidation to the substrate material. Meanwhile, the low temperature also results in compressive residual stress, low porosity, and also a little thermal degradation of the coating in the substrate material. All of these actually very desirable characteristics that usually cannot be achieved using the thermal coating process. And also recent development that has been looking at repair, manufacturing, and also remanufacturing applications uses a robotized cold spray cell equipped with 6-axis robot and turn tilt table, which we're seeing in the picture, and this is used to address the complex part repair requirements such as iron cylinder heads and also aluminium mold tool repair. Next, we're going to talk about directed energy deposition, DED. What we're looking at is actually the schematic diagram of the DED technology. DED is actually a group of additive manufacturing process that adds material together with the heat input at the same time simultaneously. The heat input can either be laser, it can be electron beam, or it can be plasma arc. The material feedstock, on the other hand, is either material powder or wire, and this powder results in lower deposition efficiency compared to metal wire, and this is because only a part of the total powder would actually be melted and bonded together with the substrate. DED actually has been successfully applied in many industries, and this includes aerospace, oil and gas, defense, marine, and also architecture. Aerospace manufacturers have been using this technology for production and also for remanufacturing of structural parts for their satellites and military aircraft. And they use this because using this technology, they can actually cut short the time for manufacturing and also remanufacturing. Usually, this process takes about 1 or 2 years, and with 3D printing using this DED method, they can just cut it short to maybe just a few months. Now for the next slide, I'm going to talk about the application that the industry has used with 3D printing so far. So the thing that we're seeing right now is railway. So Deutsche Bahn, which is a German railway company, they use 3D printed spare parts to cut cost and time on repairing their trains. Before this 3D printing method, when the company needed to service their train models, spare parts for some of the components are actually unavailable, which is why Pan actually turned to casting process to have new parts produced. Because the old method, it requires a very high minimum purchase quantity, and also the part delivery sometimes can take up to months, which will cause this method to be extremely costly and is also very inefficient. So what Pan did was approach 3D printing, and this is because these 3D printed parts, they provide the parts they need faster, and as per demand, they don't have to meet the high minimum requirement. And so this company uses wire arc additive manufacturing, and they use wire as raw materials that is fed through a nozzle, and it is welded layer by layer to create their desired product. And also this approach actually provides Deutsche Bahn with increased availability of spare parts as well as lower manufacturing costs. This remanufacturing using 3D printing also greatly reduced their downtime needed for the trains to be serviced. The picture that we are seeing is actually a 3D printed near net wheel set bearing cover, which is on the left, and on the right side is the post machine part for their class 294 locomotive. And then next we have the diesel engine parts, and the picture that we're seeing is actually a 3D printing cylinder head repair that is done by Cummins, and Cummins is a heavy duty diesel engine manufacturer that has also turned to 3D printing to produce and repair critical engine parts. The reason why Cummins chose 3D printed parts is because of after doing some research, they have found that through 3D printing, they can make parts for worn and damaged engine parts on the spot in emergency situations. They can also produce replacement parts as they need, and they also can reduce the need for mass production and also inventory storage. Cummins actually has been using 3D printing to repair cracks and damage done to cylinder heads. That is what they usually specialize on. And before using this 3D printing, they actually used to send their cylinder heads to machine shops to have the cracks removed and also to have the hole be cold stitch welded, leading to a very long downtime. Even then, this was only a temporary solution for the problem because the cylinder heads would eventually crack again. Um, this method was very ineffective, it is time consuming, and it is also very expensive. So as of now, Cummins is actually using a DED, direct energy deposition system, 3D printer with 5-axis CNC head called the DM3D machine, where the spray nozzle laser um, the spray nozzle is actually laser guided to the accurate damage location for them to repair.
Hi everyone, my name is Di Ziyuan. Today I'm gonna to present about the advantages of 3D printing for remanufacturing. As we know, products that made from 3D printing are environmentally friendly. It can be last long, easy to repair and recyclable. So, it has created a new green economy based on the remanufacturing process. In the remanufacturing process, 3D printing uses less material and creating a virtually no waste by allowing the printer to build material upon itself. Therefore, repair product can be produced more cheaply and the maintenance cost will become lower. Moreover, flexibility is another advantage of 3D printing for remanufacturing. As an example, although the broken product has a complex shape, 3D printing still can be used for scanning and restoring the broken parts. Therefore, it makes the process of restoring defective parts more efficient. After knowing the advantages of 3D printing for manufacturing, we also need to know what is their disadvantages. First, 3D printing technology is expensive due to the 3D printing equipment and material costs. It still requires higher investment costs for better development. Besides, 3D printer has lower printing speed, so it is not the most cost-effective way to repair the broken products in large quantities. Moreover, different types of 3D printing machines and process might be needed for different defective areas of broken product. Hence, post-processing is required for printing a better quality of the product. Furthermore, 3D printing for remanufacturing is restricted by the rebuild size. This is due to the reason that most of 3D printers have small print chambers, which restrict the size of parts that can be printed and repaired. As an example, anything bigger size of broken products should be dismantled to smaller parts. Then, the defective parts will be restored one by using 3D printing technology. Last, all the parts will be joined together again after finishing remanufacturing process. In this slide, it will explain about the limitation of 3D printing for remanufacturing. For the use in remanufacturing, directed energy deposition is the most preferable, useful method to restore and repair the broken object. It also helps to reduce environmental impacts and financial expenditure by extending their production life cycle. However, it has some limitations that need to be faced, such as limited materials, high cost, and inconsistent quality of 3D printed parts. Besides, during the manufacturing process, void formation between subsequent layers of materials would reduce the interfacial bonding between printed layers. This causes additional porosity on the broken product and yet reduce mechanical performance. Other than that, transferring computer-aided drafting (CAD) into a 3D printed part often results in inaccuracies and defects, especially in curved surfaces due to tessellation concept of CAD, which is an approximation of the design. Therefore, for achieving the desirable dimensional tolerance, hardness, and surface roughness, and ensuring like-new performance, it requires a post-processing after 3D printing the damaged part. Furthermore, it is hard to machining on complex geometry due to its limited tool accessibility. So, removing a cubic shape from the damaged area by machining and 3D printing on this cubic shape is a potential solution. Thank you.